Hello, in this video I will be presenting my final research project from my time at State Fullerton. This is testing the spin limit for merging black holes. An earlier version of this talk was given at Pacific Coast gravity meetings both in 2016 and 2017. My advisor for this research was Dr. Jeffrey Lovelace. Sometimes in science we want to test the limits of things, or what happens if we change a variable until something in our system breaks. Examples of studying extremes in this way can be found from Black Hat's default question, "What if we tried more power?" in Randomore's XKCD comics or What If blogs, or the Gargantua black hole from Kip Thorne's Interstellar, which is so extreme in mass and spin that it lets Dr. Thorne pose thought experiments about time travel and things. I will be studying black holes, though perhaps not quite as extreme as Gargantua. We should define what a black hole is. In general relativity, space and time are described as a single four-dimensional surface. Massive objects curve this surface, and that curvature is what we feel as gravity. Black holes are so massive that they can be considered a point and produce the strongest curvature/gravity in the universe. This is so strong that light that passes nearby is bent around the black hole. Light that happens to fall into the black hole cannot escape. Light, the fastest moving thing in the universe. If we wanted to kick things up a notch, we could make the black hole spin. Black holes have a maximum spin of 1 as defined by the Kerr metric, or the mathematical definition we use to measure the distance between 2 points near the black hole, in units where the gravitational constant equals the speed of light equals 1. This definition of curvature is the spin angular momentum of the black hole divided by its mass squared, and we define this as the Greek letter chi. By definition, chi is less than or equal to 1. Another possible definition of the spin of the black hole is to have 8 pi times the spin angular momentum is less than or equal to the black hole's surface area. We can rewrite this as 8 pi s over a is defined as zeta, and this also should be less than or equal to 1. The systems I will be studying in this research have two black holes of equal mass, equal initial chi angular momenta, and the chi's of the two black holes that are orbiting each other are aligned with the total angular momentum of the system. So the chi arrows and the L arrow are all pointing in the same direction. The limit I wish to test is, as mentioned earlier, the 8 pi s is less than or equal to the black hole's area, or we can rewrite it as zeta should be less than or equal to 1. Mathematical relativity has not proven this except in cases with axial symmetry or conserved angular momentum. This symmetry and conservation rule are broken in the cases where the black holes are recently merged, and they look more like the peanut shown in the picture on the right. How would we approach the math of this sort of problem? It is important to state that symmetry and conservation laws are related. This is Noether's theorem. We can use this theorem to write down some math. The killing vectors we define are vectors that point along symmetries and so should be related to these conservation laws. They satisfy Killing's differential equation, which is listed. This can be split into two parts, the trace or divergence, which divergence can be thought of as a scaling, growing, or shrinking operation in the picture on the right, or the symmetric trace-free part, or shear, which, if it were a fluid, would correspond to your fluid being bent over by some force. In these situations where we don't have an exact proven symmetry, we can use approximate killing vectors that will try and approximately satisfy the Killing's equation. We can set the trace or divergence to 0, and trying to minimize the symmetric trace-free part or shear should still solve our problem. One nuance we need to be aware of is that these vectors are defined up to a constant. The constant doesn't affect the solution to the overall equation because constants can come out of derivatives. Constant times vector in a derivative will just be constant times derivative of the vector quantity. So we need to normalize our vectors to figure out what this constant is. We know we need to normalize, we need ways to do that. Our preferred normalization is this Kerr normalization, defined by the equation shown, and we can cite Dr. Lovelace, Owen, and some others in a paper in 2008 in their appendix for the math on these slides. Full citations can be found in the description. So this Kerr normalization, we know it holds for Kerr or Kerr-like black holes. The z in the integral is a scalar function on the horizon associated with our approximate killing vectors. We prefer this normalization because it is computationally efficient and better tested for having low numerical error. To talk about some of the simulations Lovelace and people have done before, we can see that the zeta spin we are interested in spikes at the time when the first merged common horizon has just barely formed. And if we zoom in on that point, we can see that specific measurements of zeta at specific times from common horizon forming can be fit with a quadratic line, so the earliest zeta is perhaps best measured in between the time when we made a specific measurement and the time when we knew specifically there wasn't a common horizon. One way to do that is with a quadratic fit. For all these previous simulations that Lovelace and other colleagues did, we can plot this earliest measured zeta as a function of the initial chi spins of the black holes in our simulations, and we notice a linear trend. This trend predicts that for initial chi's on the black holes of 0.998, we will get a common horizon with a zeta of greater than 1. For most fit in between the earliest time methods, quadratic or Hermite polynomials, but not necessarily for earliest time step. The earliest time step prediction is about 0.992. So we might very well wonder, what if we tried more spin? That's what I did. I ran measurements of a recent simulation with these initial chi's. The simulation was actually run by a colleague, Matt Giesler at Caltech. My measurements of the spin of this simulation show that the earliest zeta is 0.999261, which is higher than the prediction from the previous earliest time steps, but noticeably is still less than 1. To get a better comparison, we might flip the axes and rewrite time in units of time minus the time when we first found a common horizon. 0 is now the time when our software first measured a common horizon, and small numbers counting on from there. So we can add an orange line that shows the latest time without a common horizon, and that would be time t-1. And we can speculate that the common horizon should be somewhere in between these two. This should only illustrate with the red ellipse that the common horizon forms in between t1 and t-1. The difference between these two, if we convert to standard units, is about 1 nanosecond if the total mass of our system is 70 solar masses between the two black holes. So within 1 nanosecond, a jump of zeta from about the red ellipse to 1 seems rather unlikely. So we might wonder, is this normalization specific? Are there ways we can trust that our normalization is getting accurate numerical results? So the first step is to use a slightly different normalization. There are two options in the software. Both are detailed in the Lovelace-Owen paper from 2008. So if we use the other option, we can see that the other option finds zetas greater than 1. That might be concerning. First things first, does it do that for other simulations? And it does. We can see that the non-Kerr normalization keeps zeta greater than 1 across different spatial resolutions, all with about a % difference between the two normalizations in the single digits of %. Rather than just making comparisons and worrying ourselves, we should try and get some specific numbers to figure out how well these algorithms are working. We can compare spatial resolutions, as the % difference was showing. Spatial resolution 2 minus 3 over 3 times 100 should give us a % difference between our different levels of spatial resolution. Or we can find horizon surfaces as a series of spherical harmonics. That's how our software models the apparent horizon surfaces. These series should converge with more terms or a larger small l number. To put some intuitive pictures to all that math, spatial resolution is just more boxes in a grid. If, hypothetically, Lev 2 were one box, Lev 3 could be 5 boxes on a side, Lev 4 could be 5 boxes on a side for each of those boxes. So for each increase in step in spatial resolution, we are adding more little boxes on our spatial meshes for the software to solve for things. Angular resolution with few terms in the series would be like a circle. And as we add terms, you can get more detail on the angular surface, so like ellipses, peanut-shaped things. That is perhaps the more relevant sort of resolution to care about. So then to actually test that our algorithms are converging with more resolution, we should try running with more resolution. So when we compare spatial resolutions, we notice that the difference between spatial resolutions is about 10 times smaller for both algorithms than the difference between the algorithms. This is true for both comparisons of different spatial resolutions on the somewhat older chi equals 0.994 simulation. So that gives us at least a small amount of confidence that it's not algorithms misbehaving. For the more relevant angular comparisons, we also used the same somewhat older simulation, but increased the number of terms in our series. And we can see that for the yes normalization, the difference in comparing one resolution with another drops towards 0 at an exponential rate. That gives us confidence that the yes normalization is converging and behaving. For the no normalization, it fits with a linear convergence trend, if at all, really. That is significantly less good of the algorithm, and besides, it might have other errors when we talked to Dr. Owen about it, so we won't worry too much about that one, because it might be inaccurate and it's computationally intensive and takes a while to converge besides. In a bit of a summary, we measured the spin zeta of merging black holes using approximate killing vectors. The preferred Kerr normalization preserves a measurement of zeta less than 1, which stands to contradict the linear trend prediction from Lovelace's earlier paper. The other normalization does not, but has demonstrated concerns. It doesn't converge well, and like I said, Dr. Owen is concerned that it would have errors anyway. Future work on these would be to make measurements on an updated simulation for the highest spin case. That now has more resolutions, so these sorts of convergence tests could be done on the high initial spin of chi 0.998. It would be a good idea to update our horizon finding script, since the updates to the underlying software mean that that measurement script doesn't work anymore. And of course, in the farther future, we might like to try more spin. That's about it. There's a spare slide for questions. I am happy to discuss questions related to each video in that video's comments section.